Nu ben je er.
Okay, one more time. Good evening, everybody. It is a great pleasure for us as Koninklijk Natuurkundig Genootschap to have tonight Professor Dr. Filippo Fraternali as a speaker. And I would like to introduce him very briefly to us. Filippo Fraternali is a professor at the Kaptein Astronomical Institute at the University of Groningen, and his main interest is understanding galaxy formation. He obtained his PhD from the University of Bologna in Italy, and then went to do postdoctoral research already in the Netherlands, but also in the UK, where he was a Marie Curie Fellow. Before he came to Groningen, he has in fact been a professor at the University of Bologna for 11 years. But then he chose Groningen, probably because it was a much nicer place. Certainly not for the weather. He has made key contributions to understand gas accretion in galaxies, so the key supply to feed the formation of new stars and to let galaxies evolve in our universe over a timescale of 14 billion years. He is an excellent teacher, as you will experience in a short moment from this lecture, but also it's proven because he received the PhD Supervisor Prize at our university, and also he won the Astronomy Teacher of the Year award. And he recently published a textbook, Introduction to Galaxy Formation and Evolution, which is very much appreciated. His outstanding research has also been recognized by the Humboldt Foundation and the Royal Astronomical Society by awarding him the Friedrich Wilhelm Bessel Prize and also the George Darwin Lectureship. So we are very happy to have him tonight to tell us about the 14 billion year journey of the gas that fuels galaxy evolution. Please, Filippo, take it away.
Thank you very much, Inga, for this very nice introduction, and welcome everybody to this lecture. I'm very happy and honored to have the chance to tell you about this journey that brought the universe from the primordial gas, as we will see, to beautiful galaxies like the one that you see in the background. And I apologize that my lecture is going to be in English. My Dutch is not yet at the level for this kind of lectures. Maybe in a couple of years I could consider it. The subtitle of my talk, this 14 billion year journey, tells us already that the age of the universe is about 14 billion years. This is precisely 13.8 billion years. And I remind you, given that I know a bit of Dutch, that this is a myriad in Dutch. It's not biljonen, which is something that confuses me sometimes. So our universe is a universe that makes galaxies, makes them grow, makes them evolve, makes them flourish. And there are galaxies come in very large variety, among the most beautiful galaxies, in my opinion, are spiral galaxies. The Milky Way is one of them. And here you see a couple of examples. These galaxies have a very nice spiral pattern that you see very clearly from these images here. They contain stars, they contain gas, they contain dust, they contain all the chemical elements, they probably have planets. Their structure is very much the structure of a very thin disk that you see very well on this other image here of a galaxy that is almost seen age on. And the star, the gas are rotating in this disk, and we will come back to rotation at the end of the talk, which is a very important property. The disk is very thin. In fact, you can measure that it is as thin as a compact disk. Today. So they are also called star-forming galaxies. And this, you see it here, for example, in the star-forming regions that are sort of colored in purple here. So very, very efficient at forming stars. And why are they doing that? Because they still have lots of cold gas. We talk quite a bit about cold gas in this talk, which is very important. It's the fuel of star formation. And here we see the gas not at optical wavelength, like in this image here where we see the stars. We can see the gas at radio wavelength with this transition that is very important. It's a 21 centimeter emission line that shows us the distribution of hydrogen, atomic hydrogen in this galaxy. And you see that the gas is much more extended than the stars because these two images are on the same scale. And the image that I'm showing here is really a classical picture that has been obtained with this fantastic instrument that is the Westerbork synthesis radio telescope that has been operating for 50 years. As you can see here, it's a nice picture of the inauguration of the telescope with the Queen and Jan Oort. They are working together below one of the antennas. And here you see this telescope today, still fully operational, as I was saying, after actually a major upgrade that has been completed essentially in the last few years. Another type of galaxies that are in the universe are called elliptical galaxies. And these are significantly different from the spiral galaxies because these are passive. They are not forming stars anymore. They look very smooth, as you can see, and they have formed lots of stars, but in the past. And these galaxies, they tend to be located in so-called clusters of galaxies, like the one that you see here, which are enormous structures where many galaxies are very close to each other, so very high density regions of the universe. And these galaxies also tend to be very massive, more massive in general than the spiral galaxies. On the other side of the spectrum, when we go to smaller galaxies, we have the dwarf galaxies. And these are much smaller than a galaxy like the Milky Way. They can be 10 times smaller, 100 times, 1,000 times smaller, and so on and so forth. And they all come, they both come in two varieties, star forming, like this one here, or passive. This is just to give you an idea of the variety that we have in the universe, in the current universe today. And galaxies are also interacting with each other. And sometimes these interactions are extremely strong to the point that the two galaxies end up merging with each other. This is, we say, when they essentially really join into a new structure, which is a new galaxy. Here you see in this nice simulation that gravity is bringing these two galaxies joining with each other, merging, we say, with each other, and effectively forming a completely new galaxy that most likely would be an elliptical galaxy. So this is a channel of formation for elliptical galaxies. And the last thing I want to say about galaxies is that they are really many, many in the universe. And this is a way to show it. This is an image taken with the Hubble Space Telescope, and it is this is an incredibly long exposure of a tiny fraction of the sky that you see the fraction up here that shows an enormous number of small points, and every single point here is a galaxy. And we can have an idea with this movie. So these are the constellations that make the impression of how tiny is this part of the sky. And then we know the distance of these galaxies. So this movie goes through these galaxies very quickly. This would be much faster than the speed of light. And we get to the last one that we see here, that is so far away that the light has taken 12 billion years to reach us. And we can also estimate now how many galaxies there are in the universe, and the last estimate tell us that there are about 2 trillion galaxies, and this would be billion. This is a schematics that essentially capture the title of my talk, the journey between gas at the very beginning of the universe. This is the Big Bang, and here you see in this blue part of the universe that there is essentially only gas, very simple gas, as we will see in a second, and then the whole process of galaxy formation and galaxy growing, galaxy evolution take place, and in the end we end up with the beautiful galaxies that we saw before. And the most important, one important thing that I want to say about the galaxies is that when we talk about galaxies, it's not that we are talking about a variety also within the galaxies, because in the galaxies there are stars, there is gas, all the elements that we see on Earth. There is dust, there are black holes, there are planets, etc. And one measure of the distance of galaxy, and also the looking back in time that I will be using throughout this lecture, is the redshift. We use redshift very often. The redshift is essentially a measure of how much the light from a galaxy has been stretched due to the expansion of the universe. And that tells us essentially that the more distant is a galaxy and the more further back in time is the light that we are observing from that galaxy. So redshift measures both the distance and the time with respect to us. So you see in this plot here, redshift 0, just to have it clear in mind, I will repeat it, but redshift 0 is now, so this is the present day, 13.8 billion years, as I was saying. Redshift 10 or 20 is more or less the epoch of the beginning of galaxy formation, okay? So when the universe was less than 1 billion years old. Okay, so how to make galaxies? This is the recipe to make about 1 kilogram of galaxy, and it won't work because obviously you need much larger quantities, but the ratios are correct. So you need 150 grams of gas, and this gas is incredibly simple because there is essentially mostly hydrogen, 110 grams, and 40 grams of helium, and just a little bit of lithium. And then you need quite a bit of dark matter, 820 grams of dark matter, and that's it. You obviously before have to prepare an expanding universe. It's very important to do that. Then you have to mix the ingredient and fill the universe, let it expand for 14 billion years and serve immediately. And this is more or less what happened to us. We were served this wonderful universe to look at and to try to understand in the very last period of this 14 billion years. And the other point that I like to make is that so helium, hydrogen, and lithium were produced right after the Big Bang. But they depend, and their ratio, their quantity, etc., by many things, by the density of the universe, the laws of physics, the type of elementary particle, the rate of expansion, many things. If some of these things were different, well, then we would have had a different universe. And this is an interesting food of thoughts that I'm just throwing there. I'm not going back to this point. Okay, so let's start from the early stages of galaxy formation. In these stages, the dark matter plays a very important role because the dark matter produces these so-called dark matter halos, which are a concentration of matters that start to feel its own gravity. So the universe is expanding, but within a dark matter halo, at some point, gravity managed to counteract this expansion. So the matter is at that point, so we say gravitationally bound, okay? And so this victory of gravity is the reason why we have galaxies. Otherwise, we would not have them. And if we now concentrate on one of these dark matter halos, inside actually there isn't only dark matter, there is also gas. But gas has a fundamental property that is different from dark matter, is that it can cool, meaning it can emit radiation, essentially. And this makes this gas losing energy. And when it loses energy, it concentrates in the center of the dark matter halo because it is attracted gravitationally. And that is the place where the proto-galaxy can eventually form. And in the proto-galaxy, the density of gas would be high enough that also the first stars in the universe can form. And this moment of star formation is really important. So let me stress it a little bit more. Stars form essentially out of the collapse of cold gas. And this collapse is due to the gravity of the gas cloud, the self-gravity of the gas cloud that then reaches in the inner regions, higher and higher densities, until essentially the densities are such that a protostar is formed and the nuclear fusion starts to take place. So the criterion for this star formation has been discovered actually more than 100 years ago by James Jeans. And this is, you see, the beauty of very simple equations. It says simply that when the mass of a cloud is larger of the Jeans mass, what we call the Jeans mass, then you are prone to gravitational collapse. Of course, the Jeans mass has lots of physical meaning, but the criteria is simple and to some extent is not so precise, but it's very useful. It's still used today after almost 120 years. And so what happens also in the early universe is that in this more or less in this period here, as I was saying, between redshift 10, redshift 20, redshift 10, which means something like half a billion years or a few 100 million years after the Big Bang, the first proto-galaxies and first stars are forming. Okay, now what happens next? Next, the galaxies have to grow because those proto-galaxies are extremely small. And the way they grow through infall of gas from what we can now call the intergalactic medium. The gas is continuously falling into the dark matter halos, and then eventually this gas will also reach the proto-galaxy. And if we now concentrate on the galaxy, in this galaxy there will be an accumulation of gas, and so there will be also star formation. And star formation brings to a number of consequences. By the way, this medium, we call it now interstellar medium because it's between the stars. So star formation has a number of consequences. One is that it builds the stellar component of galaxies. That is the one that we were seeing before in the photos that I showed you at the beginning. The second one, very important, the stars are actually producing all the chemical elements that we see around today. We started at the beginning with hydrogen and helium, essentially. And now we see many more elements. They all come from the stars. Then some of these stars are exploding as supernovae. And this produces what we call supernova feedback. That is an ejection of material that can actually even escape the galaxy and so creates these outflows. And now we are in a situation in which there is inflow, there is outflow, so the whole system becomes quite complicated. And then in several galaxies, essentially, for sure in all the massive galaxies, dwarf galaxies, we are not sure, in the center there is the formation of a central black hole. And this also, once in a while, explodes in as it doesn't explode, it has very strong releases of energy, and this we call it black hole feedback. So the point that I want to make here, though, that all this is what we understand, but in practice, seeing this gassing flow that comes into the galaxies is extremely difficult to do, especially at the moment with the current instruments. But we know that the gas fuels the star formation. And so one way to see that the gas is coming into galaxies is to see how many stars form in the universe. And this is a representation of the star formation rate density in the universe from the beginning of the galaxy formation, so redshift 8, here you see 13 billion years, to today, okay? And this peak here, you see, there was a moment in which the universe was forming more stars. It's called cosmic noon, because in this plot looks like in the center of the time. But this plot is not really in good function of time, because you see the 10 here is sort of in the middle. If you put it as a function of time, the plot looks like this. And so you see that the peak is not anymore in the center. This is not really noon. This is early morning at most. And this tells you better that the galaxy growth is actually very short, a few billion years. And then you have very long decline that we can call galaxy evolution. And so the region where we are here now is that is here in our plot. So the galaxy are growing around redshift 4 or something like that, and then the cosmic noon will be around redshift 2. Okay, then how does the evolution of a galaxy proceed? And this depends on the type of galaxies. And a way to put it is to say whether a galaxy is in a hurry or not. So there are some galaxies that are in a hurry, and they essentially form stars very quickly, and they consume all their gas, and to the point that they go to this process that we call quenching, which means that the star formation stops. And these are the elliptical galaxies. Why do they do that? There are probably several reasons. We think that part of the problem is that the gas that they have becomes too hot, cannot cool anymore. The black hole feedback may have a role. These galaxies are also most probably produced by merging, so this is another important effect. Other galaxies take it more easily, and these are instead forming stars, but at a reasonable rate. And these are the spiral galaxies, and who can have kept forming stars for the whole age of the universe, so for 14 billion years, and we see that they are forming stars even today. Why do they do that? Because they have kept some gas cold. Star formation needs cold gas, but also because they somehow are keeping this gas inflow working. And so gas coming into the star forming disk that we see here. And also mergers have not been very important. So in the next part of the talk, I'm going to concentrate on this gassing flow, which is a very important phenomenon for these galaxies. And this is particularly important, as I was saying at the beginning, because the Milky Way is one of them. And so we also want to understand how the Milky Way has managed to keep forming stars for a very long time. Okay, gassing flow. So I said at the beginning that there is an intergalactic medium around this dark matter halos, and the gas is flowing into the dark matter halos. This is relatively well understood. We know even more or less the rate at which this inflow is taking place. But coming into the dark matter halo is not the same as feeding the star formation, because this picture here is now more or less to scale. So the galaxy that is inside the dark matter halo is much smaller than the dark matter halo. It's at least 10 times smaller in radius, even smaller than that. And so the gas doesn't only have to come in here, it has to go through all this journey and arrive to the very center of the halo. And that takes quite a bit, because it takes at least 1 billion years, and many things can happen in 1 billion years. So the ideas that we have is that this can occur in 2 ways. The first way is so-called cold inflow. So the gas comes in with filaments that are very efficient at penetrating the whole halo of the galaxy and reaching the galaxy at the center. And this is as the pro to be very quick. So very quick in this context means 1 billion years, not 10, and which is relatively quick given the distances. But as the con that seems to work only in the early universe. So this would not explain how spiral galaxies keep forming stars also later on in the evolution of the universe. The other possibility is called hot inflow. In this case, the gas comes in, but as it comes in, essentially it gets heated up. Even if it were in a filament before, this filament breaks apart, and the gas, it's heated at a much higher temperature and creates what you see. This is a simulation. You see that this very hot region around the galaxy that would be here in the center. We call it hot atmosphere. This atmosphere is stable. We stay there for quite a while. But to form stars in the center, it needs to cool, because stars form out of cold gas, and that may take quite a long time. So this is a process that can work throughout the whole universe, not necessarily in the early universe, but takes long time. So maybe problematic from your point of view, and we don't completely understand yet how this gas can actually cool. And we can look at this actually looking at the history of the Milky Way, taking the Milky Way as a representative of spiral galaxies. So the Milky Way was born more or less in this period here, as I said, between redshift, around redshift 10, let's say. But it definitely didn't look like this. It looked like a very small proto-galaxies, like you can see in this hydrodynamical simulation. Here you see a blow up of the center, very small and a bit messy proto-disk that is rotating, and then filaments of gas that are coming into the disk, bringing gas. And in fact, the beginning of time, where the beginning of the evolution, we think is characterized by this cold inflow. I call it cold inflow epoch. And so with these filaments, and this would last for more or less a few billion years, as you see up here. But then at some point between redshift 1 and 2, so sort of 9 billion years ago, the hot inflow epoch starts. And this is quite long, because I said it's about 9 billion years. And so this means that most of the stars that are in the Milky Way should have formed in this hot inflow epoch. So it is very important that we understand how this hot gas can actually cool and feed the star formation in the galaxy. Even more so because the sun was born there, right in the middle of the hot inflow epoch. So the sun, for the sun to form, cold gas was needed in the disk of the Milky Way, and this gas had to come from accretion, going hot and then cool, most probably. Okay, so Yes, the last thing that I have to say here is that this is, as I was saying before, this is, however, a theoretical, mostly reconstruction of what happened in a galaxy like the Milky Way. What is the gas inflow history of the Milky Way? Because it is extremely difficult to see gas inflow directly, and we can hope to start seeing it in the next years. As I will say a bit at the end. Okay, the last part of my lecture is about, as I was saying at the beginning, another fundamental property of gas, which is, and galaxies in general, which is rotation. What do I mean with rotation? Well, we have seen the spiral galaxies. We said that they are disks, and these disks keep themselves in equilibrium because the gas is rotating very fast, actually, around the center of the galaxy. And so it is very important to understand where this rotation comes from. And thanks to the work, in particular, of the Canadian astronomer Jim and Nobel Prize winner Jim Peebles, we know now, we understand that this, the spin of galaxy, the rotation of galaxy, what in physics we call the angular momentum, comes from the very early formation of the dark matter halos that I discussed at the beginning. This is because the dark matter halos not only feel their own gravity, but they also feel the gravity of the halo just beside. And if you have a structure that is not perfectly round, well, this gravity, you see, will impart what we call a torque, but you can imagine a spin. And so the halos will start a little bit spinning. And if you have a proto-galaxy that is forming there at the beginning, in the middle of the halo, well, the galaxy also will feel this, this effect. We call it tidal field, and will generate the spinning of the disk. And this was actually studied before we understood where it was coming from, first by Jan Oort in the Milky Way. He really understood the Milky Way in the rotation in the Milky Way in great details. And then here I'm showing him in this nice pictures, nice photograph when he was a student in Groningen at the beginning of the last century. So rotation is a very ordered motion, but galaxies don't only have ordered motion, they also have chaotic motions. And this I'm showing it here in this sketch here. So if you have a cloud that is rotating only, this would be the pattern that the cloud makes around the center of the galaxy, let's say. But if you have on top of the rotation also chaotic motion, then the cloud would jiggle around and there would be the rotation would be very different. We can quantify this the amount of regular order motion, the amount of the chaotic motion. We do quantify it with this ratio that we call it V over sigma ratio, where V is the rotation velocity and sigma is called velocity dispersion and is related to turbulence. So when this ratio is high, so 10 or larger than 10, then the galaxy is very regularly rotating. When this ratio is close to 1, then the chaotic motions are very important. And when you look at galaxies nearby, you see that the galaxies nearby are actually very regularly rotating. And this is something that here, for example, I'm showing with one galaxy. Again, here you see the stars in optical, the gas, H1, 21 centimeter. But the 21 centimeter also gives us the velocity of the gas that I'm displaying in this picture here that is called velocity field. So the velocity field, you don't have to look at the details, but you see that there is one side of the galaxy that is blue. It means it is blue shifted, is coming towards us. The other side is red shifted, is going away. Is what you can expect when the gas is rotating regularly. And in fact, the fact that this is so symmetric from one side to the other tells you that this rotation is very regular. So a cloud will go around like this. Now we have so if we get if we measure V over sigma here, it would be equal to 15. So very very high. Now, I was saying we have simulations that can reproduce disks at redshift 0, so in the current universe, that are more or less similar to the disks that we observe. You see that they are rotating regularly. This is one example. But if we take the same simulation and we go back in time and we see what this simulation predicts for early galaxies, well, this is the prediction that you see is extremely chaotic. And you see up here, we are at redshift 4, 5, so 10 billion years ago, essentially. You don't see the disk. It's extremely chaotic, lots of things happening, lots of accretion. So if we measure the V over sigma predicted by this simulation, this would be clearly 1, even less than 1. Now, the reason why I'm telling you all this story is that in the last year, we have obtained, for the first time, observations of galaxies in another emission line, that is an emission line of carbon, very precisely, with very high accuracy, and we could construct for the first time this velocity field. This is a galaxy at redshift 5, so very long time ago, and you see that the velocity field is incredibly regular. This is another example, is a galaxy at redshift 4. This is gravitationally lensed, so it's more complicated. But what you have to look at here, you have to look at this velocity field, and you see that this is also extremely regular. And these are two publications that I've done with collaborators of mine that were published in two very important journals, Science and Nature. And they are essentially showing that in these early galaxies, the V over sigma is actually 10. So these are much, very ordered. They are, the gas is in a very ordered rotation. And this is very much in disagreement with what the models are predicting right now. And these wonderful observations were produced with this instrument, which is an interferometer in the Atacama Desert in Chile that is operating right now. And we'll have many more data in the next years. But there are also extremely important instruments coming in the near future. The James Webb Space Telescope will be the successor of Hubble that should be launched at the end of this year. This extremely large telescope that will be a telescope, as you can see here, as big as the Colosseum, something never tried before, a factor 4 almost larger than any other telescope on Earth. This should come online in 4 or 5 years or so. And then from the radio side, the square kilometer array that will be built throughout the 20s, going out to 2030. And this telescope really is promising us to see the gas inflow into galaxies, the one that I was telling you before, we struggle very much to see right now. Okay, and this brings me to the conclusions of my lecture. I showed you that, our universe is very efficient at making galaxies, although in the end, the recipe for the beginning is extremely simple. You need lots of dark matter and a bit of very simple gas. Gas inflow into galaxies is fundamental because it fuels star formation and it makes the galaxy keep going with this process until today. And we have seen that early galaxies actually are much more ordered in their motion than what we thought until now. And with this, I thank you very much for your attention.
Thank you very much, Filippo, for a very interesting lecture. So I see we have two ways in fact how you can pose your question, you can use the question and answer part if you're in the Zoom, or you can post a question also if you watch this via YouTube. So I have both channels open and I can see the questions. So I see the first question actually posted by Wilfried Alsem. He thanks you also for a very interesting lecture. So just like me. And then he says, dark matter is not really matter, according to Erik Verlinde, but the result of compensation of entanglement entropy where real matter originated. And that is why there's actually locally more dark matter where there's visible matter, such as galaxies. You talk about...
I mean, this is one recent attempt, but there have been several alternative theories also in the past. The real problem is that there aren't models of galaxy formations really with theories without dark matter that can reproduce galaxies at the level that the cold dark matter theory is able to reproduce at the moment. This could be also this, but the current situation is that the best model that we have, the one that gets closer to the universe that we observe, is a model in which dark matter is made of particles, and in particular of this massive type of particles. Doesn't mean it's the right one.
Okay.
I hope I answered the question.
I think there's a lot of speculation about dark matter out there. In fact, the second question is also about that by Ludelai. What is the role of the dark matter?
So in this picture, the main role of dark matter is to attract gas. So the galaxy formation without dark matter would be extremely slow because there isn't enough gravity, essentially. So dark matter produces. You can look at gravity in general relativity terms as a deformation of the space-time. So dark matter produces this deformations, if you want, where then all the matters can fall into, and in particular gas, and so accelerates galaxy formation at a level that is compatible with what we observe. So dark matter seems necessary to have galaxy formation as early as I was saying, so a few million years after the Big Bang, as it is observed. So that is the main role in terms of galaxy formation, but then also for galaxy evolution, this gravity role keeps being important, because, as I was saying, the gas is falling into the dark matter halo because it's attracted mostly by the gravity of the dark matter. So I hope
okay.
this.
Thank you. I don't see any questions at the moment. I do have one myself. So it's very nice to see these two results that you have now about the gas motion. So that probe actually that even a long time ago in the universe, the galaxies were already rotating quite regularly. So I was wondering, of course, you looked only at two galaxies. Of course, it would be nice to have more, but could there be also a possibility that not all the galaxies undergo this irregular motion? Because you put it very strong that we have to completely rethink the way how the galaxies form, but how strong is that evidence based on two galaxies out of 100 billions of galaxies?
Exactly. No, very good question. The reason why I put it a bit like this is that I know that there are more galaxies like this. In fact, we have collected now, let's say, 10 galaxies that have essentially the same value of V over sigma measured. But there is a general property of all these galaxies that they are very massive. So they are very, very, for that redshift, they are particularly massive. They would be, we are considering them the progenitor of very, very massive galaxies in the current universe. So large elliptical galaxies. And so the question is it a property of these very massive galaxies, while when you go to smaller galaxies, for example, a progenitor of a Milky Way galaxy would be much more chaotic? That is difficult to establish at the moment, but in principle it's not impossible. ALMA is capable to observe also galaxies at smaller masses. So in the near future, I think this will be actually addressed. Okay,
nice to hear. I see another question by Lou Delay. How much gas is left for further galaxy formation? Can we go on forever? So I presume especially the Milky Way.
It's a very good question. Actually, most of the gas now is not in galaxies, is outside galaxies. So there is still lots of gas. The question is, will galaxies be able to make use of this gas? This is not easy to answer because it depends on many things. But most probably the gas that is really around the galaxies, so not in the intergalactic medium very far away, but closer by, we call that medium the circumgalactic medium, which is, I mean, within the dark matter halo, the round thing that I was showing in gray. That gas can be potentially used in the future. And that gas, in principle, for the Milky Way can double the mass in stars in the disk. Although the future is difficult to predict because also, I mean, there are some galaxies that at some point, for a number of reasons, as I was saying, stop forming stars. And so the Milky Way can go in that direction. Actually, the Milky Way is launching itself against our neighbor galaxy that is called Andromeda. And so in something like 3-4 billion years, we will actually collide with Andromeda, and that will probably be the end of our nice spiral galaxy. We will turn into something else.
Well, so, I think we will not be there to witness that.
No, you and me, Inga, most probably not. But this actually can happen before the famous expansion of the sun and everything. Yeah. So that you know, this is very difficult to predict. But
let's see how we treat our planet in the meantime.
Yes, exactly.
So there's a question by Marco. Is there any other interaction between dark matter and the inflowing gas probably than gravity?
Yes. So in general, I'll answer between dark matter and ordinary matter. That's also a very good question. So we are the working hypothesis at the moment is that the dark matter interacts only via gravity because we don't have any evidence that would be otherwise. But again, it's still an open question. Certainly, the dark matter doesn't emit lots of radiation. If it emits a bit of radiation because of annihilation of some process that have been proposed, this is quite difficult to see because we have searched for that and it's not very easy to see. So mostly gravitational, yes.
There's also a question by Wilfried Alsem. Galaxies look like and rotate like a CD disk. Is there also a preferential movement or rotation in the universe of galaxies with respect to each other?
let me first I say something about the C disk, because the CD, because when you look in details, actually a CD rotates is a solid body, and so rotates as a solid body, right? But the galaxy actually does not rotate in the same way. The galaxy is called as a differential rotation. So the inner parts rotate faster than the outer parts. And so you can imagine different rings that they are rotating at different speeds, to some extent a bit like the solar system. And so you don't have to imagine it as a solid body. That was my only point here. Then the question is if there is a preferential movement or rotation in the universe of galaxy with respect to it. So rotation in the whole universe, as people have tried to look for angular momentum in the whole universe, but has not been found. Galaxies are moving with respect to each other quite a bit, because there is the general expansion of the universe. That's the substrate movement, if you want. But then galaxies have peculiar movement with respect to each other. And so, for example, there are these very big structures that are called galaxy clusters, that I showed one of them. And in the galaxy clusters, the gravity of the cluster is so strong that then galaxies feel more the gravity, the interaction between each other and the gravity of the cluster than the expansion of the universe. And so the motions there are completely dominated by the gravity in the cluster. And if a galaxy gets close to another one, things can happen like in the movie that I showed. So they can merge, and they can, like in the future of the Milky Way I was saying before.
Mm-hmm. And there's one more question by Piet van der Kraut. If rotation results from tidal interaction of dark matter clumps, why does the gas rotate along? Does the dark matter drag the gas along?
So here, I guess you are referring to the initial the tidal torques that galaxies are acquiring at the beginning. There, the idea is that the torques are acquired both by the dark matter and the gas essentially at the same time. So it's not the dark matter that is dragging the gas, but it's just matter that is feeling the gravitational pull of neighboring chunks of matter. And if this matter is not distributed in a spherical way, this gravitational pull produces this initial spin that then turns into a rotation later on. So it's a gravitational effect also for the gas.
Okay, thank you. I don't see any questions in the YouTube channel. Otherwise, I would have reported them. Are there any further questions to Filippo? If not, I have one more question, because you mentioned the James Webb Space Telescope. So can you maybe say whether, you think James Webb Space Telescope will have some results on this kind of rotation and influx of gas at very early stages, or is it more to do population studies of galaxies at high redshift? So what is the key area where James Webb will actually give us new clues?
So there are several, but the one thing that I had very much in mind related to the last part of the talk was to try to understand what are the properties of these early galaxies that we are seeing rotating very fast, that for which we don't know anything about the stellar component, because the stellar component, given that these galaxies are at a very high redshift, so redshift 4 and 5, the light from the stars that is coming from that galaxies is stretched into the infrared, and actually is almost mid-infrared. And so to observe them, we don't have a telescope at the moment. And the James Webb will be the telescope to observe the stars there. But James Webb will also give us kinematic information also about these galaxies. So yes, these are the two things that I'm most looking forward.
Okay. So yeah, well, I think we had a very lively discussion. So I would like to thank you one more time, Filippo, for this very nice, entertaining lecture and also for the lively discussion we had afterwards. So thank you very much.
Pleasure.
And thanks everybody for listening in. And I think that brings us to an end. George, is there more to say?
No, this is the end.
This is the end. Well, we hope to see you certainly back at the next lecture that we are organizing. So it was great to have you all, and we hope to see you again next time.
Good. People can leave and they can see the title of the next lectures.